Welcome, everyone. Welcome to the US-RSE 2023 conference tutorial, Introduction to Software Quality Practices for Reproducibility. Today, we are very happy to have Milewicz and Miranda Mundt here to give this tutorial, and Christian Gilbertson will also be here to help TA. First, I'd like to remind everybody that we do have a code of conduct that we ask everyone to follow for your reference. Right here, give that a read. And if you're not yet a member of the US Research Software Engineering Association, would like to become one, you can join on the US-RSE webpage at this link here. Now, this is a hands-on tutorial. I'll be acting as moderator and keep an eye on the chat for questions in case you get stuck. But since we have a lot of people, help is offered on a best effort basis, meaning the instructors won't necessarily be able to spend a lot of time with a single person or stop the tutorial. The tutorial is being recorded, so you can follow along at your own pace once it's released. As a reminder, the material for the tutorial is available in the Google Drive folder for this tutorial, which I am also putting in the chat. And with that, I'll introduce Reid and Miranda. Reid is a computer scientist and software engineering researcher in the Department of Software Engineering and Research at Sandia National Laboratories. His research focuses on developing better practices, processes, and tools to improve software development in the scientific domain. Miranda Mundt is a research software engineer and member of technical staff within the Department of Software Engineering and Research at Sandia National Laboratories as well, with an interdisciplinary background in applied mathematics and economics. As a practitioner, researcher, and consultant, she works closely with scientific software teams across diverse domains, including climate science and optimization modeling to advance software engineering and scientific computing. And with that, go ahead and get started.
All right, thank you so much. Also, I want to take a moment here to introduce Christian Gilbertson, who is our postdoc, who's joined us about 3 months ago. And we are very excited to have them join us. So I'll go ahead and share screen. And this is sort of we had given this tutorial previously, or at least an earlier version of it over the summer at the ACM conference on reproducibility in Santa Cruz over the summer. And we got a lot of feedback on how to strengthen it. And once again, this is a learning opportunity for us. Much of what we're going to share today is derived from grant-funded research that we pursued to collect data on how scientific software teams approach reproducibility challenges across the software lifecycle and how quality fits into that. And we welcome any feedback you may have, comments, and there'll be plenty of opportunity for discussion. And if you have any questions, of course, as Lauren said, she'll be monitoring the chat. And with that, we can go ahead and get started.
Quick question, Reid. Are the slides going to be available?
I can make them available afterwards, yes.
Great. Yeah, so Mike, they'll be available after the tutorial.
Oh yeah, they'll all be available. And there'll be the recording as well. We'll make all this available.
Thank you.
Let's see. Yeah. And all right, we can go ahead and get started. So who is this tutorial for? So this course content is relevant both for people that are looking to learn more about best practices in engineering reproducible software with an eye in particular like software engineering best practices and their relevance to managing reproducibility sort of as a quality of software, right? But the other part of this is, and given the venue, a major focus for this is really on finding ways to promote better practices, software engineering better practices in science and engineering software contexts, right? Finding ways to try to link up things that a lot of researchers may care about, things like reproducibility, time to science, and connecting that to software engineering excellence. The learning objectives for the tutorial, and we're going to cover today, is one, to cultivate a deeper understanding of how the principles of software quality engineering can help us to create more robust, reproducible software. Then we will identify different sorts of software development practices and processes based on our studies that teams find kind of align with or help advance their reproducibility objectives. And then we're going to get into how to concretely take action by facilitating software process improvement on projects based on the productivity and sustainability improvement planning toolkit that we help co-develop. And as such, we've got 3 objectives. So the tutorial is going to be divided into 3 parts. So we're going to start by talking about software quality, then we're going to be talking about practices, and then we're going to get into software process improvement. The schedule for today then looks like this. There would be about 15 to 20 minutes of presentation. We have at each for each third of the tutorial, there is going to be a breakout group discussion and sort of an interactive exercise. Then we're going to come back and discuss the results of that. We'll do a quick recap of what we covered. Then there will be a 10-minute break. And with that, we can go ahead and get started. So first, we're going to talk about reproducibility through the lens of software quality. So we're very interested in understanding how quality engineering and assurance plays a role in the reproducibility of science and engineering software. So we've approached this from many different angles, one of which is we did a survey, both of the US-RSE and of people at our own institution, as well as various universities. We got around 200 plus responses, like 220, 230. And what we find in talking and kind of surveying as well as interviewing teams is that many people believe that quality matters, right? So what we see is first reproducibility, and which we'll get into the definition of that in a second. It's universally understood as being fundamental to their work. That is, if software is not reproducible, well, that limits its usefulness, right? Can we really trust its answers if they're not really consistent under the same input, same conditions, whatever consistent means? And 86% of respondents that we polled believe that high quality software, all things being equal, is more likely to be reproducible. That is, there's a prevailing belief that quality and craftsmanship pays off, that quality matters. And 91% said that if they were given the opportunity, more time, more funding, right, that they would be willing to spend that time and funding on improving the quality of their software to help them meet their reproducibility goals. At the same time, we also recognize that there is need for improvement in the among the community. Around 46% say that they aren't confident that they have effective practices to manage reproducibility. Half of them are on the fence about this. Half of them say absolutely not. We are not well equipped for this. 1 in 4 respondents say that their productivity is hindered by their limited ability to manage reproducibility. That is, their software breaks, it behaves erratically, and they have to spend more effort getting their code to behave consistently. Moreover, 42% say that their stakeholders don't understand the amount of time, cost, and effort it takes to ensure this reproducibility, right? This came up in a number of study contexts that we examined. We had participants telling us that, also people that were from funders. So we talked to funders, right? They said, as someone giving money to and expecting results from software teams, that there's a communication gap around software quality, right? On one hand, they can understand that, adding this capability, this new algorithm, this helps them do this new science. But with investing in something like maintainability, right? Being able to make the software easier to work with, right? It's harder there's some communication gap about what exactly that entails and what the funders are getting for their money, right? So there's definitely some communication issues. And then finally, we know that science and engineering software teams want help. 90% of people we polled said that they would like to see more training opportunities and reproducibility related topics. Hey, that's why we're here. And 66% said they wanted there to be standardized guidelines for building reproducible software, right? So taking into account the stakeholder communication issues, what we recognize is that we don't just need resources for individuals and teams creating and using their software. It's important that we try to find a way to arrive at a common understanding across this whole software supply chain about the need for investment in software quality to achieve scientific objectives. But before we kind of delve into reproducibility, I kind of want to talk a little bit about when we say quality, what we really mean, what we say reproducibility, what we really mean. So with that in mind, Software, there's a couple different definitions of software quality out there. There is the standard IEEE definition, which is the degree to which a system or component or process meets specified requirements, or the degree to which a system, component, or process can meet customer or user needs or expectations. Now, there's also a similar definition, but there's some nuance in it. The ISO-IEC definition, which is quality is the degree to which a system can satisfy both the stated and the implied needs of all its various stakeholders, and thus provides value. And we here, giving this tutorial, tend to prefer the ISO-IEC definition when we talk about scientific software. That's what we're going to be using in these exercises with the ISO-IEC model. Usually because, one, we see that scientific software rarely has formal requirements. Now, there are some that argue that they could have that, but we just know that at present they don't. So there's some tension there. We also know that scientific software developers are their own users, right? And in that sense, they are they're directly impacted by the quality of their own software as a user, also as a developer, right? Which adds a lot of nuance to how how people work with software in this domain. So we also know that when we talk about software quality, we're talking about many different dimensions of quality, different ilities here among software engineering folks like ourselves, right? So we talk about a software quality model, like the ISO-IEC model that we're going to be using today for software product quality. We're talking about that we have some defined set of characteristics, we have relationships between them, and that gives us a way of talking about and making sense of quality. Right. So that ranges from everything from functional suitability, does it implement the correct algorithms in the correct way, to performance, does it run well, to usability, can the users use it effectively, reliability, can it recover from errors, is it less likely to break, and so on, right? And before we go any further on that, we do have a poll that we would like to poll the audience here. So when you think of high quality scientific software, just saying that, what aspects of quality come to mind? Like what for you makes a piece of software high quality in this context? So if you go to mentimeter.com and you input the code 9812358, which we will put in the chat, wanted to poll people. And Christian, did you want to share slides? Share screen for the Mentimeter?
Yep. I'm doing that right now. Select window or screen. My goodness.
Sort of need to put back.
Sorry, while we're doing that, there is a question in the chat.
Yes, we are. It's current. Our survey paper is currently under review, and we have a report that's going to be coming out about it and the rest of our recent research work on this. And we'll be making that available, especially to people in the US-RSE, since they participated, for example, a lot in that survey, right? So yeah, so soon. We're just getting all of it kind of through review.
Thank you.
Yep. Yeah, 9812358. We'll give people just a minute to fill that out.
Yeah. Can people see my screen? Can you see my screen, Reed?
I can.
Okay, great. The code is also at the top.
I will let you know though, Christian, if there are responses that have come in, we can't see them.
Mm-hmm.
Oh, fantastic. Okay.
We're waiting for responses. I think people have already.
Oh, okay. Give me. I think I might have to restart Firefox because it was like it needs to allow screen recording.
That's fine. Go ahead.
I will be back.
Oh, there you are. Okay, perfect. So we got like 38 responses. I think you're able to scroll through them. So some things that people listed is that it's easy to install, that it's tested, that it's easy to use, that it's well documented. Let's see what else we got here. Easy to reproduce results. Yep. Extensible. Yeah, transparency is another one. Open source, open data. There's a huge push for open science lately, which kind of goes hand in hand with the open source movement in a nice way. There's a nice alignment there. I can actually remember how to use it a week later. Also reviewed by others. So don't just take their word for it that the code is reviewed, that the code has been reviewed. Containerization, that's another part that it's very easy to deploy in virtual environments. That's increasingly popular these days. And that the software should never fail silently. And so in some ways that is a usability concern, right? So you can think about user error protection. It's also a reliability concern, right? So the software should behave reliably and it should mitigate or make you aware of, at least make you aware of failure, right? Great. So I will come back and share screen. Sound good? So for just for comparison here, for that survey, which like we said is under review, but we're trying to get this through the review here. I believe everyone can see. What we find generally is that functional suitability tends to be a chief concern. You know, one, it should have features. Those features should be correct. It should be easy to add additional features, right, to evolve alongside the science. But also usability. We find that for nearly around 1 in 4 projects that we've surveyed, that usability is actually their top concern, right? People want to have software that the community can use, right? Not just that it is feature rich. In some ways, having the software that is more usable tends to
Reed, just so you know, you're sharing your screen and not the slides themselves.
Really? Oh, hold on.
We see the presenter view.
Oh, yeah. I don't know why I was doing that. Oh, I see what it did. Let me see. Forgive me for the technical. Yeah, let's try sharing again. So we're going to share here. Thank you for y'all's patience. But yeah, so we find that the usability is really important, and then beyond that, things like reliability and maintainability, security, of course, ranks low. That's often not something people tend to worry as much about. A smaller number that we find highly prioritize, say, something like compatibility, the ability to work with interoperate with different software libraries, or portability. But in many ways, that's really a function of what type of project we're talking about. So we find that as projects, say large software libraries, large community-driven pieces of software, compatibility and portability, of course, become more and more important because you're serving more and more users. So when we talk about quality, on our team, we tend to view things through the lens of the theory of software quality construction, which explicitly links quality to practice. So the theory of software quality construction is that stakeholders take deliberate actions to define the objectives of their software development. Then from that, you can identify quality characteristics that satisfy those objectives, and then based on those quality needs, you're setting strategies to create that quality in the software through the right practices, processes, tools, ways of designing and operating and managing the software, and so on, right? So when we talk about a software engineering view of quality, what that really means is, one, that teams invest in software quality strategically, right? So teams have to allocate finite resources to maximize certain quality aspects while balancing them against competing quality objectives and remaining flexible towards unforeseen challenges. Next, we know that quality is something that must be addressed throughout the software lifecycle. So if we want to have quality in the end product, we have to be thinking about it during requirements, during design, during implementation. It's rarely something that happens as an afterthought. It's almost always the product of intentional work, hard work to make, to implement, quality into the software, right? And this implies then that at each stage of the work, certain tools and practices could help us ensure quality outcomes, right? So we're very cognizant of the role of good software development practices in engendering quality, right? And the use of those tools and practices, of course, should be grounded in the best available evidence. We should have good justifications for why we use this practice, but not that practice, or this tool, but not that tool. Knowing what's actually going to work for us, right? And that's then what takes us to reproducibility, right? So we're going to look at reproducibility today as an ility, right? Like maintainability, usability, portability, right? We often talk about those things like in, software engineering, software quality terms, and we haven't historically done that as much with reproducibility. It's often seen as something that happens at the end, like when we're packaging the software, when we're publishing on our work, right? But it's something that we want to kind of reframe that a bit and think about how can we be looking at reproducibility earlier in the software lifecycle, right, in order to help ensure it. So there are many different competing definitions for reproducibility out there. There is the ACM trio of definitions for replicability, reproducibility, and repeatability. And those are kind of different flavors of the same thing. And the distinction is, okay, is it the team that created the software that's using it? It's the team that is not the creator, but they are using the software. Is it the same hardware? Is it different hardware? But for the purposes of this tutorial, we like the definition that was given by the National Academies of Science, Engineering, and Medicine, which is the ability to obtain consistent results using the same input data, computational steps, methods, code, and conditions of analysis, right? So what exactly those things mean, right, can vary. So consistent, what we mean by data, what we mean by methods and code, and so on. But the idea is that we want to have, this is the thing that we want to achieve. And this is a superset really of the ACM definitions. And we also recognize when we use something, we talk about things like consistent, right? We know that, you know, there are all kinds of barriers and limitations that we find in practice in trying to keep codes reproducible for whatever reproducible means, right? So first, unlike physical experiments, where outcomes may vary due to differences in equipment and materials, software is, at least in theory, it's perfectly copyable. And so, you know, you'd think it would be precisely reproducible. But as we know, in reality, there are many different competing non-deterministic factors involved in achieving high performance in scientific computing. So if you say you add up 1 million numbers randomly that you divide up between different processors, depending on the rounding you get, you may get a spectrum of different results, right? So there's inherent non-determinism, especially as we scale up. So in practice, whether you mean reproducibility in the sense of the same bits, the same statistics, or the same phenomena, it all depends on what you're willing to compromise on, performance-wise. We also know that hardware and software, is the environments in which these codes are run, they're always going to be changing. So porting your code to a new platform, that often means redesigning your code, right, to make best use of the available resources. So when we talk about reproducibility, we're also not talking about it as something that's indefinite or open-ended. When you say usability, for example, you don't say usable for all possible users for all time, right? No, you have in mind specific users and specific use cases that you want to support. Same with maintainability, or say in particular extensibility. You know, the tool can be extended, but it can't be extended for possibly all use cases. Don't guarantee everything, right? Reproducibility, we can look at it in the same way. So we're making a strategic commitment to it, right? It's not something that's indefinite or open-ended. And of course, I will, want to stress that when we say the word consistent throughout this tutorial, or any of these words, the words consistent, results, data, steps, methods, code, and conditions of analysis, all of those things are up for debate. We are not trying to say reproducibility means one thing for everyone, right? Different domains and different stakeholders can all have different perspectives on these things. So today, we're going to be looking at reproducibility in a more restricted sense, right? So as a quality of software in a software engineering sense. But we're, of course, not, we want to bring attention to all of the good work that has been done in the science and engineering software community in order to tackle reproducibility to date. So just to talk a little bit about what the current state of practice is, we know that, in computational science, we have a very rich and storied tradition in both the theory and practice of reproducible and verifiable computation. And in the past decade in particular, I'm happy to say that the community has made significant strides towards reproducibility. So from a cultural angle, right, we've seen a shift towards the embracing of open source sharing of code and data. So there's the open science movement, the open source movement that the community has been embracing. There is this interest in all kinds of tools to maintain provenance and traceability from the inputs, from your data, all the way to publications. There's been a lot of conversations with funders, with journals, to develop policies that would encourage people to share their code, make it reproducible, package it in ways that others can use. And of course, from a tooling and an infrastructure perspective, we know that teams are increasingly using containers to preserve computational environments. They are using workflows and notebooks to capture all of the computational steps involved. And of course, there are online platforms increasingly these days that help try to promote standardization and sharing of these artifacts. Now, where our work comes in with this tutorial, one of the things that we note oftentimes in this conversation, there's often a publication mindset when we're talking about this, where we have the artifacts that we produce, the software artifacts, and they are published, curated, and made reproducible when the science is complete. So we package it up, and then our concern is about how do we keep that alive, right? Now, conversely, in this tutorial, we intend to approach this problem more from a software engineering perspective. So we're looking at the software as a living thing of evolving quality, something where we're interested in the quality from the outset. So it's something that's, of course, it's complementary to all of these tools, policies, and practices. All of these things are good. We're just trying to add a new dimension to this conversation by talking about it through the lens of quality, right? So we have a quick Mentimeter poll here that we wanted to get a sense for people. Reproducibility means a lot of things to a lot of people. And the question that we have is, okay, so why is it reproducibility important? And to what extent is it important, right? And we found there's a spectrum of different answers to this question, but we welcome your thoughts on this. Christian, you want to share slides?
Yep. Yes?
That
No?
worked.
Okay.
That's better.
Okay. So
They
let's
just
see.
won't let us win.
Okay, so one of the major themes here I'm seeing is trust, right? Because, you know, if we don't trust the software, what do we have, right? There's a connection. There's a connection there between debugging, right? That in general, modern life depends more and more on software, including scientific software, right? And reproducibility means that, you know, it behaves as we think that it should and gives us the results that we expect, right? Yeah, the ability to build on past work is another one that, you know, is something that's very important, right? And that's part of the reason why we want to share software and make it available to others. And the whole idea of this open science, open software movement is that we want to be able to build on each other's work. And if the software is reproducible and it behaves the way you think it should, it's a lot easier to do that, right? But there's also sort of the professional norms angle, right? All science should be reproducible. So why should software be an exception to that, right? We should strive to the same high standards that we apply to any other kind of science or engineering, right? All right, good. Take screen share back. So when we're so the idea here is we're reframing software, we're going to reframe reproducibility in more in the terms of software quality. So basically our hypothesis is that if you have better software tools and practices, and our RSEs are very critical in implementing those on projects, ultimately we get better quality software. And if we have better quality software, it makes it easier. It's not a silver bullet, it's not a solution to everything, but it does make it easier to have reproducible and reusable research and research codes, right? But we also know that, you know, in the general sense, I think there's a general agreement here among everyone we surveyed, and I'm sure most people, if not everyone in this room, that there is some kind of relationship going on between quality and reproducibility. But the particulars on that are not so clear. So this is an example. On the right, we have sort of an example diagram that was taken from a textbook on software engineering, where we list out all the different aspects of software quality and then say how they compete, right? That, you know, performance and portability can be in tension, right? That usability and security can sometimes be in conflict, right? But we don't really have a sense for reproducibility per se, not in the literature. There aren't really any software quality standards that incorporate reproducibility into them, right? That is to say that, you know, what if the most reproducible software was also just less functional, was less portable, or maybe it's more usable, or maybe it's more expensive to maintain, right? There's a lot of trade-offs, right? But the idea here is that while we don't know exactly all of these relationships for this entire matrix, right, we do know in general that looking at reproducibility as an ility, that helps us to identify our software quality goals, right? So if you say, okay, well, if the software needs to make it easy for different users or different teams, to interact with the software to get the same results so they can replicate your results, well, that may imply usability. Then it's a question of, can they learn how to use the software? Can they use it correctly? Are they protected from doing, making mistakes and then not getting the results they thought they were going to get? And if it's a matter of saying that, well, we want to keep something reproducible, means we have to maintain it, right? So then maybe making the software more modular would help, easier to analyze, easier to write tests for. And if the software needs to last over time, that, as the software and hardware environments around them evolve, that in turn may be a compatibility question. So how do we make the software more interoperable with different APIs, different libraries, or portable? How do we insulate ourselves from or adapt easily to changes in hardware, right? And from all that, and from everything that we've discussed so far, right, when we say that reproducibility is an ility, what we are saying, one, is that reproducibility is not an absolute good, any more than any other aspect of software quality, right? Is a strategic investment. You are not promising reproducibility for all time, under all conditions, for all users, on all hardware, and so on, right? It's strategic, right? And that's something that, is a little bit, can be a little bit challenging, because on one hand, we have this kind of professional norm when we say everything should be as reproducible as possible. But in practice, when we engineer software, we're not aiming to have, the software that's perfect in every way for all time, right? It's all a strategic trade-off. But we do know, in general, we believe that high-quality software is more likely to be reproducible than low-quality software across these different dimensions of quality. And with saying that, though, we also recognize that reproducibility may align with some quality goals, but it may be in conflict with others. The most reproducible software may be less performant, less reusable. It could be costlier to maintain. And teams and their customers really are looking for better guidance on how to navigate those trade-offs. And likewise, the connection between what specific practices would actually help us, that's something we're still discovering, trying to figure out, like, okay, so what's working, right? What actually leads to reproducible outcomes and what doesn't, right? But there is a belief then that reproducibility can be addressed across the software lifecycle, that if we design our software in better ways, it's going to be more reproducible. If we implement, our algorithms in ways that are more maintainable, more easier to test and diagnose failures, right? That's going to help us, right? And across all of that, there's going to be software engineering tools and practices that we can then use that will ensure reproducibility. So if you have testable code, then you can implement automated tests. If you have some kind of test automation, it makes it easier to adopt, say, CI/CD pipelines. And all of this kind of, in turn, helps better our odds that our software will endure, that it is sustainable, that it is reproducible. So what we're going to do now, before the remainder of this talk is going to be getting into specific practices that teams use in order to manage reproducibility across the software lifecycle. We'll also be looking into software process improvement techniques that will help you and your teams to manage this. But as a foundational exercise for that, we do have a breakout group exercise that we want to try. So this is what's known as a storyboarding exercise. If this were in person, we'd have people draw things out, but instead we're going to be doing this more descriptively in slide decks. But the idea of a storyboard in general is that it's a series of illustrations or images that we have in sequence for the purpose of visualizing some set of events, maybe a motion picture or some other interactive sequence. And what we're going to be doing today is we're going to be describing or visualizing, as it were, a user's journey through their software to achieve reproducible results. So where do they start and how do they get the answers, right? What steps are involved? And the goal here, as we go, we'll be doing this in breakout groups, is to highlight the necessary quality attributes along the way. So what we're going to do is we're going to divide up folks into breakout groups. And there's instructions in the slide deck, and we're going to be stepping in and joining you in case you have questions and help moderate. But the idea is that you want to imagine think of a piece of software. It could be software that you're working on. It could be general class of software that you're familiar with, and you can decide with your group. Imagine what software you're talking about, who the user might be for that software, and say that they want to reproduce a set of results using the software. What steps did they take? They need to do from start to finish. Like they may need to install the software. They may want to run the tests. They may want to visualize results, right? And at each step towards getting those results, the question we want to investigate is what aspects of software quality are important. So with that, what we're going to do is we're going to have this breakout group. So we have 32 people. If we have, let's see.
Do you need my help to set up the breakout rooms or?
Yeah, so that would be great if you could.
Okay. So how many do we want?
So we have we have 8 available. I don't know how small we want our groups to be.
How about we do?
I agree, up to 6 per group.
6 per group, yeah.
So maybe open 6 rooms.
6 rooms, I like it.
6 rooms and randomly assigned.
And I will not include co-hosts.
Yes, and before we jump into the breakouts, I'll show people what this looks like. So what you're going to do, and I'm going to share screen real quick, just to show people, and this will take about 25 minutes. You have a storyboard. You can put your names here. We do have a reference here when we talk about quality. So like the different like maintainability, portability, reliability. So we'll be focusing on product quality today. The first step then is to set the scene. What kind of software might be used? It's up to y'all to come up with that. Who is using the software? Maybe what their background is. Set a scene for us, right? And then say what happens first. Maybe they have to install the software. What does that involve, right? And then what happens next? What happens after that? You can copy those slides if you need to create additional steps. And then there's some discussion questions for you to think about and then talk about amongst yourselves once you're done with this activity. And then we're going to come back together as a group, and each breakout group is going to share their answers, and we're going to compare and talk about that. Sound good? Yep. First activity is the storyboard exercise. And the folder will be the same number breakout room that you're going into.
Ready for me to make the room or open the rooms?
Yes, I am. Go right ahead.
Excellent. There we go.
Looks good. Well, welcome back, everyone. So thank you for taking part in a little brainstorming exercise. Main thing here is there are no wrong answers, but to get people thinking and sort of frame the activities, helps set the stage of activities we're going to be doing next. So what we can do now is we'd like to go around the room. If from each group, if at least one person would care to speak up, we can, for each breakout group, talk about what they discussed and what came from that discussion, with regards to the questions. I think we can start with perhaps breakout group 1 and then work our way through. How's that sound?
All right, well, I guess I can talk for group 1. And if anyone else wants to join in, they're welcome to.
Go ahead.
Yeah, what y'all talk about? How'd it go?
So I guess where do I start here? Do we need to share the screen, or what is?
Yeah, you can share the screen if you want, or well, actually, I don't know if we can share.
Maybe easiest if one of you guys does that, perhaps.
Yeah, that would be easier for this part. Yes.
I'll do it. Just give me 1 moment to get it up.
Yes.
Wonderful.
We've done this tutorial in a couple like different settings. One hybrid, so we had like 2 teams or something that were online, and then a bunch that were in person. So, thank you for bearing with us on this. All right.
All right. Can everybody see my screen?
Yes.
Perfect.
All right.
So we set a very high bar for ourselves. We are the developers of NumPy. And so we were thinking of us as developers and how other people might use our library in their applications is what we try to come up with. But anyway, we'll see how it went. So our goal was to make an easy to implement tool that will give performance boosts to their whatever calculations they're performing, and that they'll get results that are consistently correct. So accurate answers that, sine of 45, well, sine of 45 is the easy one. Maybe sine of 47 degrees always gives you the same answer, and it's correct with whatever it's supposed to be, for example. And our typical users are scientists and researchers, but this also is for anybody who's looking to use arrays, for example, in Python. So I guess we can move on. First things first is, as everyone knows with Python, if you are familiar with it, that you need to install or typically need to import your package. So in this case, we're using pip as our example, but there are others. So with our software, we need to make sure that it's compatible with pip so that it can be installed everywhere. So whether that's Linux, Mac, or Windows. And additionally, we have automated testing that when we are making commits to our library, that we know that our commits will always be producing those consistent, correct mathematical results that we had mentioned before, or that the installation will work in other places. So then next, our user will import and use our API to do whatever it is they want to do. So ideally, we wrote reference documentation that is both user-friendly and has helpful examples. And as like I had said earlier, to make sure that when the user is doing math, we have tests in our software that say that they're going to get the same results every time. And so that way, when they are doing calculations, they can trust what they have. And after that, ideally, they can report whatever their findings were because they did great work and were able to use a reliable software. And once they're done, other people are able to use our software to get the same answers. And that is what we talked about.
Oh, great. Great. Thank you for sharing. All right. So for group 2, I believe, James, you wanted to speak on behalf.
Yeah, so let's see. So we ended up basically using the software that I'm writing now as the case study. So I'm just going to go ahead and show people the software rather than trying to explain. So the first thing the user does is they go to a website, which they may or may not have logged into, and they get a web app interface. And this is a flood modeling system. So they go in here and they pick their favorite satellite image, they load that. And what you're looking at here is Offutt Air Force Base, which is near Omaha. And the Air Force Base is in this area. So if I zoom in, you can sort of see that they're having a bad day as far as the river goes, because this thing descending into the water here is their main runway. So what the user does, so it was a little bit fun running Zoom and the web app that's loading a lot of data, is they indicate a little bit about where the streams are and unleash the model. And what they've done at this point is they've generated a JSON input file. They edit that, that goes to a server. The server reads only that, adds some other information, and spits it back. So they have that. And then they can go and they can look for sort of areas that are low slope ground where the edge of the water is. And they can drop a pin there and say, this is the edge. And, this is pretty clearly the edge of the flood. Hit update again. And now this additional data, those extra points, goes back and they get, basically a model of the flood for that entire area. And this is running on a server. And so for reproducibility, they can save the output layers, and they can also save the input data. And with that input data, that should be sufficient to reproduce this whole thing. You can save that file. You can, it gets downloaded. You can send that to some other person. So that's the model, right?
So you mentioned in your going over your notes, right? So the chain of events that you're describing, right? In some ways, you've made things easier for the user, right? Such as you're running on your server, not theirs, right? So they're not having to set things up, they're not having to run things, but it does imply certain quality needs on your end. If you could take just about a minute to go into that, then I need to go on to the next group, but I do want to make sure we touch on that part of the discussion.
Right. So the quality concerns that we discussed are basically things like, it would be very nice if the GUI didn't. Sorry, I'm going to start video. It would be very nice if the GUI didn't crash. It would be even better if the server didn't crash because of something that the user has done. So there are robustness components in there. There's a certain amount of security issue, and also what one user runs should not affect the output of what someone else did. So, the nice thing is that, the website is purely input editing and display visualization. The server gets, one artifact in, produces output. So that should be reproducible, within changes to, the input data that's stored on the server and changes to the algorithm that's embedded in the server itself. But, and then there are just, programming practices so that the server doesn't leak memory.
Makes sense. Okay, good. So it's a nice contrast there with one that has a web app and also a nice demo. So group 3, who wants to present on behalf of group 3? What did y'all talk about?
I can talk. I'm Julie. We talked about we used it. Oh, let me just start over. Sorry. I'm from NCAR, and I work on a model verification package called Met Plus, and so we use that as the basis for what we were going to talk about. And so I put a link there to our documentation, and we weren't sure exactly what the question was going at for what kind of software is being used. So we described the product and said the code that it uses. As far as the results that people are looking for, statistics or metrics for data set comparison, comparing forecast to observations, for example. In terms of reproducibility, why it's important, there didn't seem to be anything like distinctive about this, just the general things that you would want from reproducibility. So that's what we put there. Who is using this software? What is their background? Who are they? There are lots of users, NOAA, the UK Met Office, Bureau of Australia, universities, Air Force, Navy, lots of users are using this verification package. And that's it for that one. Thank you. So first, the user needs to install the software or use an existing build that we put on various machines. Either community machines or NOAA machines are the typical ones we install on, or they can install it themselves. More people at universities would typically do that. What aspects are important here for this step of the work? Easy installation on various platforms, from high performance computing systems to laptops, individual laptops. One thing that helps in this process is having quality documentation, both for the installation process itself or for using existing installations. How do they access those? And then maintaining current software dependencies, for example, you don't want to have a very old version of NetCDF that folks aren't using that's going to conflict with what they already use, and you want to just kind of make sure it's all up to date. In terms of the next step, we talked about need to be able to, I said ingest the software, that should say data. So I'll go back and fix that up in a minute, or thank you to whoever's doing that. Ingest the data. And then one thing we always like to encourage users to do is plot the data to make sure that the data that you're starting with is what you expect it to look like. So you don't get to the end step and wonder, hey, this doesn't look right, but it really started from the beginning before you actually did anything to that data. So that's a good first step. And then in terms of what aspects of software product quality enable this step, you have to be able to read in a variety of input data files. For example, NetCDF compliant data, GRIB2, ASCII formats. Those are just a few off the top of our head. And then provide the ability to convert gridded data formats to the same grid, because it's really hard to compare data if they're on different grids. So that's just two examples we came up with. We really rushed through the end here, so I'm sure there's a lot more that we could have put there. And then the next step is to utilize the tools to analyze the data and obtain the desired statistical output. So the aspects of software that enable this step of the work are extendability, the ability to add on functionality easily, add statistics and metrics that that the users need and want. Having maintainable code, again, really, so it's easier to make it extendable. Coding standards help with that for new people coming onto the team, the ability to jump in there and read the code as well. And then quality documentation, both for the users and the contributors, and including best practices.
Great. All right, sounds good. Thank you. All right, so group 4. Who wants to speak on behalf of group 4?
I can speak. So, where are we? Okay, so in our case, set the scene. We imagined that we were writing a software to do genome assembly, specifically looking to do long read assembly for Oxford Nanocore. And in the context of something like this, why is reproducibility important? If you're doing an assembly, ideally, if you have the same set of reads, you should get a similar or same assembly, dealing with stochastic and random variables and all that good stuff, but it should be highly similar. And in the context of medical and genome applications, reproducibility is quite important in terms of just safety and privacy, and maintaining the data for the user. So who's using the software? Researchers, medical applications, consumer, commercial, genealogy for the most part. So what happens first for this user? The user is going to have a set of reads, and they're going to expect to output from that set of reads an assembled genome. So what aspects of the product are going to make that possible? It needs to be performant, of course. This is a pretty heavy analysis to do, so you need to be able to have code that's going to get it done and not take the rest of your life. To do that, you'll likely need to use idiomatic coding to the language of your choice. If you're coding in C++ or Python or Rust or what have you, the way that you code is going to make that software much easier to maintain in the future. And most of the time, it's going to result in more performant code. And in terms of usability and portability, for a user that's first running this software on their data, they might want to test it locally. They might have like a small set of reads that they want to just do a quick assembly on, see what kind of very initial outputs data they get from there. So the code you write should ideally be able to run locally, or at least compile locally, and be easy to access and install, whether on your system or on the server or HPC or wherever you happen to be running your analysis. So then what happens next? Okay, so the user has used the software, they have their assembly, but as is the case with many tools in this field, the formats of the files are going to be really important for downstream analysis. So the output of this software that we're writing needs to be regular or standard, such that it can be easily converted to the formats that are going to be needed for other tools. And same thing coming from the other end. There could be various kinds of inputs, different kinds of reads that we would want to put in. We mentioned specifically an Oxford assembler, but we might want to branch out a little bit more and have options to include reads from other assemblers, or maybe perhaps in non-standard formats. But that's something that we'll need to plan, and that's something that the user might want to have available. And then finally, is this a package? How is this going to be released for our users? And what aspects of that make it possible is, are we planning to release this on CRAN or on PyPy? Is this something that we need to add extra bindings for to increase portability? Is this something that is likely going to be called as a subprocess or as another wrapped function from a different programming language? And that tends to be the case in this field. So it's something that we want to plan early. And finally, as the users getting more involved with the software, testing out different parameters and stuff, we want to make sure to have developed a human usable interface. Whether it's the CLI or the GUI, it needs to be something that the user can pretty easily work with and learn from and adjust their program arguments without causing a headache trying to figure out what each flag does. All right, and then finally, so now what happens after that? This we're imagining in the context of a few months or a year later. This assembly software the user is going to want it to be maintained. So if they're planning on updating to the current version, they should be able to do that. The update should happen smoothly. It shouldn't crash. Trying to do the update. And it should be able to run still. Ideally, some users, they might even want to keep the current version they have, and that current version should still be able to run. If they were to need to, erase it and then reinstall it from the repository or what have you, that existing version should still run. Scalability, we kind of added in as a thinking, would the user want to scale this up? Are they trying to get more assemblies done, larger assemblies on more complex genomes? How do we do that? And that's something that definitely we would need to plan from the beginning. So what aspects of software product quality enable this step? Built with specifics and compatible with environment management, definitely. Ensures some kind of backwards compatibility, at least to the point that if we were to try to install an older version with all of the dependencies and data that it came with, that it would still install. And that at this point, as the user is continuing to use the software, that the error messages continue to be useful, that they are valid for updated versions of the software, and that the results that we output continue to be correct across all different versions of the software.
Mm-hmm. Sounds good. All right, thank you. All right, so breakout group 5. If you want to take 2 to 3 minutes just to summarize what y'all talked about, what they're here. And then we'll go to 6, and then we'll just recap and then take a break.
Yeah, okay. I can summarize it quickly. So we've got a similar topic than James. So we look at simulation, but in this case, social simulation. And we've been focusing on the models that you build for software that you can buy. So the software is called AniLogic. And we chosen some use cases just to explain what social simulation is. One would be testing emergency exit in an airport, that you model all the people and their behavior and how they, when the alarm sounds, try to get out. So these are the kind of models you can build with this software. And what we are looking when we use this software is we have different scenarios that we are running, and we try to work out which is the best option to get most people out. And sometimes you have counterintuitive solutions that you didn't think about before. When it comes to publications, it's very important that actually your models are well described so that they are reproducible. Very often we have problems with reproducibility because people don't make the data available. So data are required as an input, and that stops reproducibility. What did we say as well? So the tool itself is very expensive, and there are other tools that people use, and that's normally for the reproducibility very important that you can adapt it to the different tools. I don't know, could you go to the next slide? Yeah, thanks. It's very important for these kind of software that the modeling comes first. So you would start offline like you do in software engineering, where you use analysis and design before you do an implementation. You would actually build a conceptual model first and then implement it. And hopefully you have all the data that you need. Yeah, I think that's the main things. Yeah, we didn't get anymore.
No, you're fine. I think you covered. I think you had to cover multiple steps, like right in there that you.
Yeah, exactly.
Out on the first slide, which is fine. That's exactly what we need to do.
Good.
So that's great. And then one more, and then we'll kind of summarize and recap, since a lot of people are bringing a lot of interesting things to this. Who wants to speak? Just take 2 to 3 minutes to speak on behalf of Group 6.
I guess I'll go ahead.
Sure.
For our group, we just kind of came up with a generic example based on like Elizabeth's experience on just like the data visualization and analysis, pipeline software where folks, input some data and get some output from that. So we kind of identified that, with this, people are looking to get some visualization and analysis, and reproducibility is important because a lot of times people are, maybe picking up this code or project, then haven't worked with it before. Someone else was developing it initially, like in a research lab group setting. And it's important to be able to get the same results, when you want to reproduce, some, report from a paper or something like that. And, often these people are coming from different backgrounds and have different levels of experience. So some people might just want to use the software. Some people are looking to contribute to it. So, people's experience levels are going to be a little bit different when using this piece of software. So the first thing that kind of happens is that folks are going to just need to build and install the software if they don't already have it available. And that kind of poses like a lot of challenges often because it, is only built for one environment. So things like portability and compatibility make just, reproducing that initial building an installation just to be able to use the software, a little bit more straightforward in the first place. And then now people want to use the software, they're going to have to, load in some data and produce results. And, often the data might be formatted in a way the application doesn't expect, and reliability helps, recover from that, like producing error messages that are understandable. So you could, put your data in the right format, and also just, some documentation, helps users understand like what your input needs to be in the first place. So they might not even encounter those issues if they're able to read and understand how the program is expected to be used. And after that, this may or may not happen, but someone might be looking to make changes to the software and provide improvements, additional functionality, and things like maintainability help enable those changes. Portability helps enable distribution of the code. So perhaps instead of just like providing a source code, you want to produce, some packaged version that someone else will use. This often happens for publication when you need to, provide like the methods along with your results. And, reliability helps make sure that any changes you make don't break any existing functionality that already exists in the code.
Great. So thank you all for sharing this and engaging in this activity. So what we covered here in the first section is looking at reproducibility through the lens of software quality. We kind of gave a refresher on software quality definitions, how we define things like reproducibility. And what we find in our studies, and I think we see here as well, is that when we look at what it takes to get reproducible results, we can break that down into different quality needs, right? So many groups here identified that the software needs to be installable, so it needs to be maintainable, it needs to deliver results in a performant way. It needs to be, say, interoperable with, say, a visualization tool so that they can actually know if their results are the results they think they have, right? And different users and different projects may have different quality needs around reproducibility. But by reframing it in this way, it makes it easier for us to take action, right? It's easier for us to think about what kinds of steps that we need to take in order to ensure, or help maintain the reproducibility of our codes, right? So what we're going to do now, and thank you all for sharing. We're going to take a 10-minute break, and then we have a second section, just really talking about software practices, and then quality and the relationship of those practices to quality. And we may have a short activity then, and then we're going to look at software process improvement, and we're going to talk about, in the final section, about tools that you can apply with the teams that you work with, the projects that you're on, in order to precipitate and engage with the team on improving their practices vis-a-vis reproducibility. So thank you. We'll all just be back in around 10 minutes. That sounds good for everyone. All right. Okay. All right. So we can go ahead and get started back. Welcome back, everyone. So what we're going to do now, Christian, did you want to you wanted to steer and share slides, and I can. Do you want to present a part of this?
Yes, I am doing that as we speak. I was just okay. Okay, so that's doing that, but instead I want this. Great, and we can close that.
Perfect. All right. Well, welcome back. So in the first part of this tutorial, what we talked about was examining reproducibility through the lens of software quality. And what we're going to talk about now is more focused on the practices, the things that we can do in order to help ensure that the software can function as needed to help ensure reproducibility. And we're going to talk through this. We're also going to talk to a lot of our own research findings that have come out of the studies that we've been conducting. So this is under review currently at various conferences. But Christian will lead that portion. So next slide. So as you recall, we talked about the theory of software quality construction that posits that stakeholders collectively must define the objectives of software development for whoever we consider to be the stakeholders. Through that, one way or another, they are essentially identifying quality characteristics that are needed to accomplish those overall objectives. And then finally, they set strategies in their practices, their processes, and tools in order to create that quality. So if we think about reproducibility as an objective, or possibly as an aspect of quality, depends on how you want to define it, from that, and what we saw in the activity that we just did, is that there's all kinds of quality characteristics that come into play when we talk about how do you get reproducible results. And what we're talking about in this section then is knowing that there are these aspects of quality, how does that then relate to practices? How do we thread the needle, right? And that's what we're going to be talking about here. So we'll go next slide. So on our team, we do a lot of work with many different teams in many different domains, science and engineering, in order to help facilitate their process improvement. What you'll see here is in our own research center, we provide sort of a tiered approach to software practices. We help teams adopt things as they move along. Like if they're just getting started, certain basic things like version control, team policies and procedures, we try to get them to adopt. And then as we move forward, we get them over with testing and then documentation and so on, right? But the question here then is, we have all of these kind of good practices, good software engineering practices that we as RSEs can recommend to teams. But in what ways might these things be helpful for reproducibility? And that's, a question that has often come up when teams say, I want to make it easier where we're not just rushing at the end and trying to package up our software and containerize it and whatnot for a publication. I'd like to make this automate or make this process easier, right? And they come to us with questions about that, about how to make their software more reproducible, right? And so with that, next slide, we do have a Mentimeter question. Same link as before. So that would be 9812358. Question is, for your software, if you were working on a software project, I know many of you are, you have more than one. what would you do to make life easier in terms of reproducibility? What would you want to work on? If you were given funding, like additional funding, staffing, anything you needed, what would you do to make life better when it comes to not having to worry about reproducibility? Okay. All right. Yep. Have a containers, variety of tests, stronger, more robust infrastructure for doing that. Bringing everything into line with common standards makes everything more manageable. Testing by integrations of testing is pretty frequent here. Improving documentation. Okay, access to fancy cloud platforms that gives you more control over the environments in which this is all being run. Documentation, automated testing. All right. So having good code review practices, that's something that's come up often with our own research, with our own teams. Tutorials, that's another one. Being able to explain to the user, okay, so here's how you go through and run our software. It makes it a lot easier for people to, get the results that they want. Great. Okay. So this is a question that we've been very interested in for a long time. And in the past year, well, that's interesting, there's an error. It should,
oh, sorry.
Fine. I don't know why it renders different for you. Well, it says on top that it says design thinking workshop, survey, and case study. So what we were interested in, and in the past, the slides are not, apparently Microsoft PowerPoint is not reproducible. I am running it right here and I can see this text just fine, but the same text on Christian's computer is not working. So irreproducibility. But so in the past year, we got grant funding to study these things in more detail. So we were interested in seeing how different people talked about and defined reproducibility. We looked at how reproducibility related to software quality, and that comes out in this tutorial, as well as identifying practices and processes that align with reproducibility. And the end goal of this, and this is what this tutorial represents, is a lot of knowledge and work that we've done with teams at our institution in order to help them, right? And to try to build materials like this tutorial to help convey some of that knowledge. So what we like to do is talk a little bit about, we looked into these things. We looked into how different teams understand the relationship between quality and reproducibility in our survey and our case studies and all of that. And I'm going to hand it over to Christian, who's going to talk about, talk about those findings, what kind of quality aspects matter, and what kind of specific practices that teams recommend. And I'll hand it off to you, Christian.
Great. So as Reid was talking about, we had all these research activities that we did this past year. One of them was conducting an explanatory case study of 9 computer science and engineering teams at Sandia to identify software quality practices that these teams take with respect to reproducibility. So we use case studies because as reproducibility and its relationship to other qualities is understudied, it would be difficult to remove some of the phenomena from their context. So we recruited an ensemble of different stakeholders at Sandia, spanning both the scientific software chain or supply chain in different domains. And we hypothesized that the scientific software stakeholders value both software quality and reproducibility. So even if they may not have a clear understanding of the connection between the two, we believe the teams at Sandia have adopted software quality practices that align with the reproducibility objectives. So the case studies consisted of 3 interviews. First, an interview just figuring out what these projects are and kind of like what their main purposes are and what practices they use. The second, kind of like honing in on the specific practices for software engineering and reproducibility. And the third one was kind of like synthesizing those two together, where teams selected a specific practice and created a progress tracking card, which we'll actually be doing later. Which are just structured documents that list concrete steps towards a specific productivity or sustainability goal. So as part of these case studies, we asked our partners to identify or to participate in a preliminary online survey, which asked them to rank software quality characteristics according to their perceived relevance to reproducibility for their project. When we asked them to explain why. So across these projects, there was a general consensus that maintainability reduces the cost of repairing reproducibility. Usability ensures that different users will be able to get consistent behavior from the software, and reliability makes it more likely that software will deliver reproducible results when run. So we also, in addition to the case studies, ran a wider survey where one of the things we asked respondents was, if we gave your projects more time, money, and talent to invest in their software quality to support reproducibility, how would they spend it? And we found there's general agreement that if given this choice, they would make their software more maintainable, reliable, and usable. Sound familiar? That they would not invest in making their software more performant or more secure. Although security was not really considered relevant by 80% of our respondents. So just as a caveat. So yeah, we found in our work that teams are struggling, that while some teams struggle with reproducibility, others are doing better. And that's not purely a function of funding. Amongst our survey respondents, those who said that they had the right knowledge and skills and access to like peers who also knew about this, who they could learn from, and those who had more software development experience were in a better position to kind of make their software more reproducible. So the question might be like, what are successful teams doing differently? And so we looked at a bunch of different practices that we found in our case study partners and asked, what do they do to sort of make their projects reproducible? So we find that the successful teams have developed specific strategies across the entire software lifecycle to ensure that their end product is more likely to produce reproducible results. So some examples we've pulled out are, one of the projects we worked with uses documentation as a form of reproducibility pledge. So they're saying this is what we commit to supporting, basically. And they have examples and tutorials in their documentation, and they even have a book that's like, if you see this example in the book, that will definitely work. And they're like making a very strong promise of that. Another project said that for important changes, they have multiple code reviews from a domain science perspective, from a software quality perspective, which can make it easier to catch bugs, both in like code and like what you're actually trying to do. And it also helps everyone stay on the same page of like what the software is what you're trying to do with the software. And finally, we have one of the projects which sort of proactively seeks out research in their field and builds automated tests around that to confirm that their software is sort of staying up to date and doing the things that people want it to do. So this table shows which practices each team explicitly mentioned in the case study interviews. And taking all of our interview data together, we discovered that version control, automated testing, and documentation were seen as the primary contributors to better reproducibility. So all of our teams used automated testing, which offloads the critical responsibility of running tests from the developers and ensures that tests are run, and allows teams to iterate more quickly. And documentation, such as written documentation, code comments, tutorials, and code standards, make the code easier to understand for both users and developers. Our teams did use stuff like doc strings, wikis with explanations and tutorials, in that book that I already mentioned. And finally, every project used version control systems or source control management tools, and often paired it with a software publishing tool like GitLab or GitHub. And participants asserted that version control was fundamental to building modern software. We also identified several themes from these case studies. So one cross-cutting theme for many projects was this idea of communicating intended use. So projects used their practices like testing and documentation to show how they expected their software to be used. As we mentioned earlier, developers like to learn from others. People are more likely to listen to recommendations from someone they know and trust. there's a necessity for multiple domain experts. For all parts of the software lifecycle, a universal consensus amongst the projects was that more and varied expertise was better, and that reviews and expertise or experience were needed to ensure that the software stayed high quality. And that finally, people should use the right size solutions. So while certain practices such as version control should be used like from the get-go, other practices can be introduced at logical times. So that leads us to our fourth Mentimeter question. When do you all think that groups should be thinking about reproducibility when they're building their software?
Yeah.
So I will.
How early? Yeah. So
Yeah.
different teams tell us, different things about when this is a point of concern for them. At what point is this at what point do you care about this, right? At what, from day one, right? Some people, might think it's as early as requirements. Other people think, well, as soon as design. Other people think, well, while you're implementing it. Always, day one. Okay.
This
Okay,
feels like a bad talk to be asking this.
I know, right? Everyone's already, we're preaching to the choir here. Yeah, before you click create new repository, right? Day zero, before anything. Yeah, okay, but that's another point. So one interesting nuance there is when it's version 0.02. So when you know that you're going to use the software more than once, and that's something when we talked about the tiered software quality practices, what we find is that there are a lot of projects that are very low tier, very experimental. Maybe they don't go anywhere, right? And they don't necessarily want to adopt a whole bunch of heavyweight practices and tools and set up CI/CD pipelines just for this one little code, right? Yeah. Before things written, during design, though, yeah, design could be considered part of that reproducibility process, right? You'd be thinking about that. That's not for need. Okay, one person disagrees with 0.02 version 0.02 answer because it may be too late. Okay, all right. So
do you think we could go to like an ACM talk that's talking about a new like performant compiler and be like and put this at the end of their talk and see if anyone's like
a comp cert or something. Yeah. So one of the things that the universal thing that we heard from all of our case study partners for all of the practices they adopted was, in retrospect, I wish we had started this sooner, right? And I think that's kind of understood here as well. The idea is that certain practices that we've been looking into appear to be more helpful, right? In the sense that there are certain common things that they're doing, like they're helping them maintain awareness of what's going on. It gives them more control over the behavior of their software, or makes it easier to communicate to other people what they're working on, how the software is supposed to be run. Here are tutorials, here's documentation, here's a user interface, right? And all of these things ultimately result in people getting consistent results in that software more often, which is what we're after, reproducibility, right? So in this sense, we're making the argument here that by investing in these things, investing in software quality, investing in good software development practices, we can make concrete, realistic progress on these really hard problems like reproducibility. So if you want to go to the next slide. So we want to do a short breakout here, maybe 15-20 minutes. We'll try for 15 and then get back to it. In the final part of this, what we're going to be doing is we are going to be working together in these different breakout groups to try to put together or think through adoption plans or practice improvement or process improvement plans, right? For how people could adopt these sorts of practices. But to set the stage for that discussion, this is something you were already getting into at the start with the storyboarding. We'll talk about what kind of software development practices do you believe help the projects you may be involved in, and where would you want to see improvement on your various projects, right? What are the kinds of things you want to focus on? Now, in the slide deck, we did note there is a short online self-assessment tool. There's a link to that. You don't have to fill that out. That was just a recommendation to help get people thinking, but it sounds like many of the different breakout groups already have a pretty good idea about what they want to do, what they want to talk about. So with that, we can break out for about 15, 20 minutes, and then we'll come back and have a discussion as a group.
We want to use the same rooms.
Yeah, same rooms is fine.
Okay. They still look all about even. It's good.
Good.
Is there a slide deck for this one that we're editing, or it's just we're talking about it?
There's one that you can use that if you'd like, just to help scaffold the discussion.
Okay, in that same Google folder.
Yeah, the same Google folder. We'll be jumping around the rooms to make sure everyone's doing well.
Thank you.
No problem. Okay, welcome back, everyone. That's about everyone in the rooms. Yep. Okay, so what we can do now is just take just say 1 to 2 minutes, perhaps, for each group to go over what they discussed. Group 1, if you'd like to nominate someone to speak on y'all's behalf.
I was asked to go again, so I'm going to be talking again this time. I don't know if there's really anything to share in terms of the screen, so I'll just kind of go over quickly what we did.
That's fine.
So in terms of important aspect quality, just the first slide was we had decided usability, maintainability, and then performance and efficiency were the most important for our projects that we work on. So one interesting one perhaps that we had left off was reliability. And while that can be very important in some fields, if it's not safety critical, you know, if your software crashes and all the user has to do is click X and open it again, it's not that big of a problem. But certainly it's not so fun. But you know, if usability, if they don't know how to work with the software or are incapable of, or you know, you have to interpret things. Then for them, that's a problem. Maintainability was important because often we give software to other people. So if we're working on it, we want to be, if we're going to be fixing problems that they may encounter, we want it to be maintainable for ourselves so we can upgrade it. And then lastly was the performance, efficiency, and optimization. And that's make things run faster where we can, because that's the most important goal. Is we need to do millions of calculations, and if it takes forever, then we can't even make any progress. So for the next slide, monitoring performance along the way was something that we said was important for reproducibility, so that perhaps if whatever code you're writing is slowing down over time, then perhaps you're not doing something right, or that you have other errors in there that you need to be checking out. Test cases, I think everyone knows, are important, and communicating with users along the way, so that we can find out what the problems are and perhaps write tests for them in the future, so that we can be sure that we're getting the right results, since exactly what the end user is looking for could vary based on the person. And if you're not a domain expert, you're not going to necessarily know what the user needs. And lastly, things that we would improve. There's not always time to write lots of tests, so that would be great if we could have some more time to do that. Security improvements where that matters. Again, many things aren't security critical, unless it's a web-facing application, you're not going to necessarily have to worry so much about SQL injection. And communication with users throughout the software process. It's hard to say that's ever perfect. So I think, and with how critical it is, since again, other people are using your software, it's very helpful if they have a voice throughout the process.
Okay, great. All right, group 2, want to share? A couple minutes, 1 or 2 minutes. You're currently muted, Alex.
Thank you. I thought I hit A as well, but So we talked about a couple of different things, but I think for each of our projects things were different, so it was a little bit hard to explicitly say which is the absolute most important. But I think what we all definitely mentioned in one way or another was this correctness or validation piece being really important, and also the usability for not only developers, but non-engineers and others who would be potentially using the code. We also kind of briefly discussed, how performance and resource efficiency could be really beneficial for some of our projects that are running on these or doing very complicated things that require a lot of time. So, improving those can be really helpful. And then talked a little bit about portability, although that one was a little bit more open-ended, since portability can mean lots of different things, not only working on specific types of hardware, but also just working on even more than one machine. And again, that was kind of dependent on what project, whether or not that was most important or not. For the second slide, we started off with discussing, making some sort of steps to define what your terminology is up front, so that way everybody's on the same page. This, not doing that can lead to a lot of complications when you're discussing your code or even trying to implement something. We also talked about making design decisions before you start doing anything, especially the coding. We also discussed testing in just the most basic part, as well as automation would be really helpful for achieving reproducibility, as well as defining consistent standards between things. So one thing that came up was the mention of scripts and passing those off between people. For like my project specifically, we have scripts that were written from 7 or 8 different people, and everybody had a completely different idea of what that script should do. So expectations weren't really there in between scripts. So having although they're supposed to be playing well together, so having some consistency was really important. Also, doing incremental development rather than trying to do really big things all at once, but trying to do just the small bits that you can get done more quickly and implement those into your code base more quickly. And then for the last slide, we talked about agreement and buy-in to code reviews, how sometimes the bottleneck for that is just having the higher ups buy into it, or any of the practices for that matter. But we also talked about having long-lived branches being a bad thing, that they should be not long-lived and should be merged more quickly. So again, this kind of goes into how much you want to put into your feature that you're trying to add right away. So again, the kind of more incremental development would be more ideal. And then also we talked again about testing and just having any of it, but even more beneficial is once you have it, making sure that it's automated. And then also, again, with design in mind, what makes a good test, and making sure you have that discussion before you start writing things.
Good. Okay, so group 3. Now, in the interest of time, I do want to save a little bit of time for the final activity. So if you take a minute to go over this, I'm making notes on the highlights, everything you all are discussing. Group 3, you want to share? Take about a minute.
Well, I guess I can go. Julie did the last one, but for the interest of time. So I guess the aspects of software quality that we thought were most important were things like portable and easy to set up developer environments, automated testing and documentation. For open source code in particular, having well-developed policies around community management, things like pull request templates that enable code reviews. I think that was the key. and that enables you to streamline your code reviews and encourage those. There was also a component of like simplicity in the code and how you use external frameworks in a way that is the least likely to break, even if it may not be the most optimal choice in a performance standpoint. So we kind of touched on the trade-offs you were talking about earlier, Reed. And also good communication in the group that develops it. So the practices that we feel would help our project, and we kind of focused on that first slide for most of it. So it's kind of, I don't know if we should actually read these, but automated testing and documentation, and then balancing communication time and time focused on code development were the practices that we felt could help our project achieve the reproducibility. And the practices we would like to improve, yeah, I don't think it's fair to read these. It's kind of a repeat of slide one. We stuck on slide one for most of it.
Gotcha. That's fine. Well, great. So group 4, I know 2 people had to leave. They messaged us, so I merged them in with group 6. So next up would be group 5. Would someone care to take a minute just to explain at a high level what y'all discussed?
So when talking about what was used for software quality in terms of like what was most important, we had discussed functional suitability, in that there's always sort of the essential requirement that it's got to be able to do what it was intended to do. What sort of tied with that was the idea of maintainability, and something that wasn't listed, but we sort of termed long-term sustainability, where maintainability was, can you actually make changes to it in the moment, but long-term sustainability being slightly different in that whether that work is actually possible over long periods of time. So it might not be easy to work with something, but so long as you keep at it, that's a slightly different quality. But on top of that, usability was also high up there in terms of something that was very much needed, because if you're trying to disseminate it, it's more likely that people will continue to use it if they find it to be usable in the first place, as opposed to being something of an impediment to what they're trying to do. For those things that contributed to achieving reproducibility, 2 very large things were documentation, in terms of being able to reliably know how to achieve outcomes, or how to achieve results using the software, with having example use cases, very clear example use cases, being very helpful in terms of being able to sort of directly approach what it is you wanted to do, with automated testing as well, for very similar reasons that other people have already gone over, along with version control, containers, CI/CD, all of which contribute to sort of trying to offload as much verification to the computer as possible. Whereas those things that we'd like to improve were, of course, better version control practices, for, again, other similar reasons that people have gone over. For those projects that do require sort of public facing aspects, or require disseminating information but in a controlled manner, security testing is very important. And there are industry resources like the OWASP Top 10, that there's already a lot of work out there that a lot of people have spent time on that you can leverage. You don't have to do everything on that front from first principles. And again, automated testing, again, trying to make sure that you're covering more of your critical paths and whatnot, but also for environments that your code may run on, or is more likely to run on, than necessarily just on your own local computer. Trying to suss out issues that can happen at scale, as opposed to just the test data or the small data sets that you yourself use. Someone may try to run it with a much larger data set and run into issues that you never thought of.
Sounds good. All right, so someone wants to speak on behalf of Group 6. Take about a minute, then I can kind of summarize what we've been discussing.
I can speak for the group. So we were mostly focusing on individual-driven research projects, and we decided that pretty much everything listed on the survey except for performance, security, and functional suitability, which I think we took for granted, were most important. Although we did identify a reason to care about performance, which is that if your code is extremely slow to run, that can inhibit your ability to test it thoroughly. And something that we wanted to focus more on was improving dependency management and documentation. We're often dealing with time and funding constraints, so that can be difficult, as well as implementing code reviews, which require a lot of additional effort from others.
And in terms of, I see here in terms of the development practices, I see dependency management, high quality documentation, and of course having, of course, performance. Yes, it makes software easier to use. Who wants to use slow software? That of course is difficult to test. What else do we have here? And then in terms of practices to improve and why, I see writing high quality documentation, something that I think everyone would agree is important and that we don't do enough of. But also code review processes and getting buy-in on formalizing those processes. So I will note, I'm glad we're making additional time. We ended up making additional time for these discussions and for your group discussions, because I think we've had a really good participation today with these activities. I will note, I like that there's a lot of themes we're seeing here, like things that go beyond just the software tooling, let's say with automated testing, but things like community management or long-term quality needs like sustainability. These things come into play as well, right? There has been research on how do we extend software quality models to factor in sustainability as separate from all the others, right? And another thing that I've noted is, especially for those that are reporting on projects that are a little more mature or widely used, that security becomes a bigger concern, right? So that's another theme that I'm seeing here. So in the interest of time, I know that we should be done, in 40 minutes or so with this tutorial. And I wanted to make time for this final portion on productivity and sustainability improvement planning. So if it's all right with everyone, I'd like to skip the break for now, though you can break briefly after we finish this little presentation portion. I wanted to introduce you to how we do process improvement, how we facilitate it, and how this kind of intersects with these reproducibility concerns. So what I'll do is I'll share screen. So thank you everyone for sharing. And we're making notes on all this, and we might be able to do a little write-up on everything everyone shared, what everyone agreed on in all these different sessions. So all right, so what we covered today so far is we talked about reproducibility and its relationship to software quality. We talked about the practices we use, the ways we work with software, how we think about software and collaborate around it, and how it may make it easier to address reproducibility across the software lifecycle. So we saw in all these examples opportunities where we could leverage these things, leverage practices and tools in this way to ultimately give us more robust, more capable, and ultimately more reproducible software. And what we want to finish out here is on a topic we presented on in other venues before. So it's about productivity and sustainability improvement planning, or PSIP. It is a toolkit that we developed as part of the Exascale Computing project in order to facilitate process improvement with teams. And what we're going to do is talk about that and then look into, with our case study partners, as some examples about how to engage on these topics on how to improve the practices on your projects, step by step. So the focus of this final part of the tutorial is on a method for software process improvement that we've developed and applied before with numerous teams across the ECP. And it's a practice or a toolkit for realizing process improvements without disrupting current development and mitigating technical risk so you can develop software with confidence. And we're going to introduce PSIP to you and progress tracking cards, which is the main tool in the PSIP toolkit, and we can show you how you can apply them to your own project. In general, what we know about in the scientific software community is that there's an increasing interest in how do we develop software better? How do we get organized around developing software, especially community software, right? And this brings software process improvement to the fore, which in that term encompasses a wide variety of techniques for assessing, designing, and realizing effective development processes. And we're noticing these days that there's a lot of different factors that are driving this interest, right? So studies have found that researchers are spending more time developing software than they were in the past, right? There have been surveys over the years about how much time people are spending, and they say, oh, more than I was a couple of years ago, more than I was a couple of years ago. Software is becoming more and more important, right? Across many different disciplines. We also know that these projects are increasingly collaborative, multidisciplinary, and multi-institutional, right? We're seeing the rise of all sorts of community-driven software, open source software, and there's an interest in improving the quality of that software, right, at scale, and that's becoming increasingly important. And the reason for that, as software takes on a more central role in the scientific enterprise, as it has, the demand for and the consequences of that software, honestly, are greater than ever, right? We are being called upon to deliver all kinds of scalable, high-quality simulations and then data-driven analyses to solve all the world's challenges, right? And scientific software is seen as having increasingly tremendous economic, social, and political importance. So for all these reasons, we're seeing a lot of interest in methodologies and in processes that can enable scientific software developers to become more productive and to work together more effectively. And in our work, we focus on reproducibility because we see that as sort of a keystone for the development and use of scientific software. Because if it's not reproducible, then what is it, right? There's this push that we want to build more reproducible software, right? And trying to figure out how we get organized around doing that. So we also recognize at the same time that any kind of new adoption of a new tool, a new technique, or a new process, that can be disruptive. It can carry all kinds of upfront costs. And oftentimes, when we talk about software process improvement with teams, it's seen as something, they usually think of something that's formal, that's heavyweight, that's not aligned with the particular needs of scientific software projects. I have, for example, on my bookshelf at work, I have the Capability Maturity Model, or CMMI Bible, which is around this thick, and it exhaustively explains, if you're developing a piece of commercial software, all the things you probably should be doing, all of the different practices and everything. And not all of that necessarily translates well to scientific software development, though it can be useful. And what we find is, in order for teams to adopt new practices, new ways of working with their software or improving those things, that has to be done in a way that's incremental, that is integrated in how they already do their work, that is sufficiently lightweight, and that's something that needs to be iterative, where they can revisit it and adjust their plans as needed. And that's really what led us to PSIP. So PSIP, which stands for Productivity and Sustainability Improvement Planning, is a lightweight workflow. So that is a toolkit, a set of practices for software process improvement. And this is set up so that it can either be used on its own or alongside your flavors and methodologies like Kanban, Scrum, other ways of working, right? And PSIP is implemented through progress tracking cards, which is something we're going to describe. But at a high level, the goal of PSIP is to help teams figure out where they can make incremental improvements in how they develop their software, and then to realize those improvements. To give a couple examples of groups that have been using PSIP, we worked, for example, with the HDF group, who develops the HDF5 library in order to help them develop better coding standards and implement and improve how they do their documentation. We've worked with universities like Darmstadt to do tutorials. There's a lot of different teams within ECP such as Alpine and Exalt and a bunch of other application codes, where we've worked as facilitators to help them adopt better practices, right, to improve the quality of their software. And it's used quite frequently at our own institution here at Sandia National Labs. We frequently do consulting with scientific software projects to help them mature their practices and improve their software quality. So the PSIP framework, I'll just give you kind of a high-level overview of it. The idea is that it provides an iterative, incremental, and a cyclic process for improvement planning. Teams can work on all this on their own. We provide guidebooks on this and materials on this on GitHub. It's freely available. But we also do guided facilitation with teams as well. And I'll just walk you through how this process works. So what we do in the first phase is an assessment. So the teams we work with, they are comprised of world-class scientists and engineers. They are very adept at devising solutions to technical problems. That's usually not their problem. The challenging part, we find, is often in identifying what truly matters to them as a team, right? And how their software goals are aligned with what matters, right? Like they're interested in doing high quality science, right? And insofar as that they want that, they value the software and its quality, right? And so when the ideas team facilitates a piece of effort, we always start with a team meeting. We talk about their current project practices, how do they deliver value to themselves, to users they may have. Now, in the past, this was a very labor-intensive practice, both the teams and the facilitators, and we came up with a guided online self-assessment. That's rateyourproject.org. That we use in order to help step through and identify potential areas for improvement. And the end goal there is to figure out where there are barriers to quality and efficiency. So what's inhibiting you from doing what matters? So in setting goals, we encourage teams to hone in on 1 or 2 areas where they can improve in the near term, like a week, a month, a quarter, break it down into something that's manageable, right? And that's when they construct what we call a progress tracking card, which is what we're going to describe here shortly. So teams can either create a progress tracking card, which is a way of planning out these activities for software process improvement. They can either write one up from scratch, or more commonly, they consult a catalog of cards that we have online, and they tailor one to their objectives. Then finally, there's this integration step, or as we like to say, securing a commitment to action. What concrete steps can they take in a set amount of time to reach their goal, right? What can they realistically commit to doing? And here we want to see specifics, and then they enact those changes. So teams iterate on their plan, they periodically revisit the progress tracking card they created, say, how are we doing on this? And if there's any unexpected setbacks or windfalls, then the team can adjust their strategy as needed. So just to summarize at a high level what PSIP is as a process improvement toolkit, the idea is we want to have an approach to a software process improvement that's incremental, that's integrated in how they do their work, that's lightweight and iterative. PSIP is a lightweight toolkit that we've used for software process improvement that seems to work well with the science and engineering software teams we work with, and it's implemented by progress tracking cards. So what we're going to talk about now, and then there's going to be a final exercise about this in creating one, is we're going to look at progress tracking cards, which are the core of PSIP. So at the core of PSIP is what we call the progress tracking card, or PTC. It's meant to be a concise visual aid that records your intended goals, deliverables, and milestones. You create a PTC so you can progressively compare your team's progress towards some intended goal. The PTC helps keep track of your progress, as well as enabling you to probably use it or share it with other people in order to communicate what you're doing and to know when you met your objectives. And a PTC is made up of 5 components. There's usually a title, a short name that covers the topic of the card, a target, which would be a brief description of the goal you're trying to reach with the card. There's often 1 or more user stories. So those are meant to help frame the goal and provide context. These are often in the form of as a blank, I want blank, so that blank. And then the core of it in the card is, this piece right here is a numbered series of descriptions of outcomes or states of practice. It's usually numbered from 0 to 5, though the number of little states can vary, with 0 representing some starting state where the goal is not met, and the last one represents fully achieving the overall goal. And the idea behind this is that each successive entry should reflect some intermediate state of practice that moves the team closer to their final goal. We want to phrase this in a way that they can make progress each step of the way, and if they were to stop right there. They were to stop at step 2 or step 3, right? They were still better off than when they started, even if they didn't make it the whole way, right? And then there's usually a place there for comments, like any details or related links relevant to the card. So all of this is simple enough, but the magic in this process and what really works well with teams is how you arrive at these and how you use them. So normally when we do this kind of exercise with teams, they've identified something they want to work on, they want to improve practice. In this case, they want to, say, improve automated testing to support reproducibility, right? They usually get around this far before they stumble. They'll say they'll fill out X, the goal is we achieve whatever X is, and they have a user story, something like, as a developer, I want X, so our project has higher values of X related quality, right? They will list out where they are now and where they, where they feel they need improvement. And then they have a general sense for where they want to be, right? And then in the middle, they get lost and it gets really confusing, right? And this is because this is what we call in the social sciences, we call this articulation work. It's the work that makes work happen. It's about explaining what are we really here for? What are we doing? What can we really achieve, right? And that's where it's usually most challenging for teams. And when facilitating these kind of activities, there are a number of questions that we ask, like, did the team actually reach a consensus that this thing was important? Sometimes we found it's the senior leadership on a team that wants something, but everyone else on the team might want something else, right? And having those conversations is really important. And this is a way to bring that into the surface. And even when they're in agreement about what they want to do, they may have different views as to why they want it, right? For some, it might be that this thing helps reproducibility. For others, it might be that automated testing just makes it easier to add more features without breaking existing things, right? And then the final part, and once we kind of identified that, that's when it becomes easier to talk about 3. So that's what is achieving this into what is achieving, in this case, automated testing entail in practice. How do you get there? So this is a tool for dialogue. We sit down and we work with teams and they talk out their issues. And this is just sort of an artifact that reflects that consensus. As for what makes a good process improvement goal, in general, we aim for things that are collaborative and team-oriented, because ultimately, whatever it is, the whole team has to own it, right? It's very easy to roll out a new tool, a new method, but it's guaranteed to fail or fall into disuse if only a few people on the team are really on board. And moreover, the improvement activity, it needs to align with the values and the priorities of the team. So for example, I worked with a team that wanted to adopt a continuous integration solution, but it wasn't important to them simply because it would make their code more stable, but because rapid feedback on code changes would ultimately reduce their time to science. That right there, that was the real goal. And there has to be buy-in on the why. Next, a PTC, this is something that should be measurable and specific. So adopting or improving how you're doing your work, this needs to be tied to tangible evidence, like specific artifacts or outcomes that you know when you've made it. And then finally, a PTC should be realistic and it should be able to be realized in increments. Larger goals are fine, right? But it needs to be factored into smaller increments with delivered value. So for example, if your team has a goal of comprehensive testing, you want to specify incremental goals in making your plan in getting to that overall goal, right? That may mean, okay, maybe we need to refactor our code to be more testable, right? So during our case studies, we worked with a lot of teams to try to spell out, in retrospect, looking back, they said, okay, we've already succeeded at this. We've already done, in this case, I've got a card here they built for code reviews, right? And they said, we're really happy we're doing this because it really helps us with reproducibility. And they worked backwards and they said, okay, well, how did we get here? And this was part of our documenting this for the benefit of others, right? And so they're able to spell out, they say, well, we started with nothing, right? And in the end, at each step of the way, they say, okay, what gets us closer to having kind of a rigorous code review process, right? They didn't adopt all of it overnight. It started really simple, and then they started defining more kind of ground rules around it, building more tooling into their processes over time, right? And ultimately, they were able to adopt a set of code review practices, right, that were effective for their team and that they found helpful for reproducibility, right? Another example another example of what this looks like is with documentation, right? There's another team that really found it important to have good documentation to know what the software is meant to do, to even know that you're getting the results you're supposed to, right? So we worked with them in order to figure out, okay, so if they had to tell another team how to do this, what they would do. And for this PTC, you see that, right? They talked about the different stages you can go through, step by step. You're not adopting everything overnight, but piece by piece, how to get to good documentation. And the final one I'll mention is one on issue tracking, right? And the main reason why the team wanted issue tracking is so that they could empower their users to communicate with them, right? Because their users are like their first line of defense. If something is broken and they're not getting reproducible results, it's the users that are going to tell them, right? But also to help them shape the evolution of their software, make sure that they're still protecting the use cases that all these different users want, right? And knowing the why there was really important for them to figure out what kind of issue tracking is going to be best for our project, right? So what we're going to do now in the remainder of our time, we'll have around 20-minute exercise. Stop sharing here. So the final exercise, and Christian and I are going to come around room by room to help you all work through this, is to set up one of these progress tracking cards. So you mentioned a lot of different practices that y'all work on, things you want to improve. It would be good to pick one of them, right? And we can work through a progress tracking card. So in your directory in Google Drive, there is a template to fill out, and Christian and I will come through and check in on y'all on that. But with that, we can move y'all into the regular breakout groups, and then we'll have like 5 together.
So Reed, there are a few questions in the chat. I don't know if you already saw them and answered them.
There, I know one person's leave. Okay, the leave, perfect.
So we have something from Mark and Matthew.
The users, yes, normally, okay, so I'm glad, Mark, I'm glad you asked. I will say that on the PSIP tutorial, the PSIP is something we can give just a 3-hour tutorial on by itself, right? And in user stories, and we give a talk on this, on the use of user stories in scientific software context, where people are often their own users. So as a stakeholder, they're sort of in an interesting position that you don't often see in a lot of commercial software development, which is, where people are their own users and they are their own developers, right? So we use user stories in a more expansive way in order to capture that. And it's often about what they want from their software. I want this, or I want to have this kind of capability in place so that I can fulfill my software development goals and thus my goals as a user, if that makes sense. But you're correct that normally user stories relate to a software feature. Yes, so in terms of academic MLOps, not for MLOps as of yet, but I think that's an area where it's going to become increasingly important. We've done a lot of work both with application teams like scientific simulations and data analyses, right? We've worked a lot with those teams in order with PSIP and to implement process improvement activities. And often with the software libraries that are underneath those, we've worked with those teams as well. For the HDF5 group, for example, we were able to get them to agree to a coding standard, something that had eluded them for around 20 years. So I consider that a major victory, right? So yeah, hopefully that answers some of your questions. And with that, yeah, and it can be a selling point to PIs. That's a good point. I like that. So what we want to do now, just with the remainder of our time, we'll take about 20 minutes and then come back and conclude, is just to step through this, just to get a sense for how creating a PTC works. So there are instructions in the document, and yeah, we can send people out to their breakout groups, though we will need to move the people from 4 to 6, since there were 2 of those left.
Okay. Welcome back, everyone. Before I hand it back over to Reed, I just wanted to let you all know that we do have a feedback form. So if you could fill that out for us, that would be very helpful. It helps inform us how we might do the conference tutorials in the future as well. So with that, back to you, Reed.
Absolutely. So we are just about at time, right? So I want to be respectful of everyone's schedule. So I don't think we'll have time to actually go through each of the PTCs that people created, that we will kind of we'll send out some kind of reminder, something to that effect, or not, about what was covered and including what was discussed in the PTCs. But what I wanted to do is just say that this is meant to give you a taste of kind of how to work with teams, to sit down and try to unpack okay, how do we get from A to B, right? And I want to share one slide here just to close things out. So what we sought to do here today, right, is that we were trying to talk about the principles of software quality engineering and how that can help inform the development of scientific software, science and engineering software, including managing reproducibility, which is sort of a focal point of this tutorial. We identified different software development practices and processes across the software lifecycle that align with reproducibility objectives, everything from design to testing to documentation, and even to things like community practices, how you engage with your users. All of these things can play a role in ensuring that the software behaves consistently and as intended. And then finally, we looked at ways of facilitating software process improvement on projects, right? And how to have those conversations with teams, you know, the teams that you may be on as an RSE or what have you, right? And you know, strategies for managing that software process improvement. So with that, I want to thank everyone for taking the time for this tutorial. Hopefully it's been helpful. I know some of you all messaged us to say that it was, so that's good. And where is it still sharing? Sorry, there we go. I'm gonna stop sharing. And if you ever have any questions or comments, feel free to reach out to us. And as Lauren said, there is a survey that she's going to send around, both in that link that she just posted, as well as she'll be sending an email to all of you. If you like the format of this or any other tutorial, to get a sense for, did it work for you that was in virtual versus in person? What could we do differently in the future just for tutorials for US-RSE in general? We welcome any feedback you may have. So thank you again. Hopefully, good.
Thanks, everyone.
Thank you.
Thank you, Reed and Christian, and please relay our thanks to Miranda as well.
Yes. Yes.
Will do.
I'd like to remind everyone that the recording and slides will be available. And again, if you're not a member of US-RSE and you'd like to become one, the link is there. So thank you all for attending.